As an example of the preceding, consider this equation, which is of this form. This is just what we looked at in the preceding. We don't have to use the solution to this equation as a formula. We just want to follow the procedure, and it's a fairly straightforward logical procedure. We recognize that we have the e to the t function here, and we can do the Laplace transform. We have the convolution of the t function and the f of t function. So everything should work out fairly well. So the Laplace transform of f of t should equal the Laplace transform of t e to the t plus the Laplace transform of this, which is the Laplace transform of the convolution of the t function with our f of t function. Well, again, here we have the Laplace transform of f of t. The Laplace transform of e to the t is 1 over s minus 1. Laplace transform of t times any function is the derivative of the Laplace transform of that function. So the derivative of 1 over s minus 1 is just 1 over s minus 1 quantity squared. And then this is plus the Laplace transform of the t function. Now let's just note that the Laplace transform of the t function is 1 over s squared. Okay, so this is I'll do this in 2 steps. Okay, so now we have this, and now we can solve for the Laplace transform of f of t. So we bring this 1 over s squared f Laplace transform of f of t over here. And now we can express this as s squared minus 1 over s squared. Okay, and we can then multiply by the reciprocal of what we get here, which will be s squared over s squared minus 1. Of course, s squared minus 1 can factor into s minus 1 times s plus 1. So you'd end up with an s plus 1 and an s minus 1 quantity cubed with an s squared in the numerator. And you could go to partial fractions or other tricks to do the inverse transform and determine your function f.